Op-amps are the Swiss army knives of electronics. Depending on their wiring, they can boost signals, compare voltages, filter frequencies, or even do basic math. However, with so many different types available and an overwhelming number of specifications, choosing the right one can be challenging. So how do you pick the best op-amp for your project? Here are some specs from the datasheets. And that's not even all of them. Which ones matter most really depends on what you're building. For most projects, things like the number of units per package, package type, supply voltage, output impedance, and maybe even noise are important. These are pretty self-explanatory. However, most of the specs don't matter much unless you're working on something that needs high precision or really low power usage. In this video, I'm gonna just focus on gain bandwidth, product and slew rate. These are important if you're messing with frequencies that go above what we can hear. So stick around. Here I've put together a simple test circuit using an MC1458 dual op-amp, which is set up as a non-inverting amplifier. With the trim pot I can tweak the gain anywhere between 1 and 10. And that's the schematic. The first op-amp does the actual amplification, while the second one provides the ground potential for the in and output signals. With this I'm going to show you what the slew rate and the gain bandwidth products are and why they matter. But first let's have a short talk about relationships. Relationships can be complicated, especially for us nerds, right? Finding the right partner and maintaining a healthy relationship isn't easy. I know I've spent way too much time overthinking things, asking myself questions like, am I even good enough to be loved? Why do I get so anxious when they don't text back? And why do I always seem to end up with the same kind of toxic person? I've gone through all of this, and I know how overwhelming this can feel. The self-doubt, the endless replaying of conversations in my head, the fear of opening up only to be let down. It's exhausting. And honestly, it can feel pretty lonely. Trust me, I've been there. Then, the best thing you can do is to get an outside perspective. BetterHelp, my paid partner, connects you with a credential therapist to help you navigate these thoughts. You'll get matched through a quick questionnaire, and if it's not the right fit, switching is free. Therapy isn't just for crisis moments. It's about growth and better relationships. Click the link in the description or visit betterhelp.com/Dr. for 10% off your first month. Alright, let's get back to the simple things. Stuff like gain bandwidth product, also called unity gain bandwidth, and slew rate. My AI assistant Eric is going to jump in and show what he's made of.
The GBP is simply the amplifier's gain multiplied with its bandwidth. So regardless of which gain and corresponding cutoff frequency we have, this value is always the same. Thus, increasing the gain reduces the bandwidth and vice versa. So the GBP is also the maximum frequency that an op-amp can amplify. An MC1458 has a GBP of 1 MHz. So if it is configured for an amplification of 1, its bandwidth is 1 MHz. With an amplification of 10, the bandwidth is 100 kHz and so on.
Alright, let's give it a try. I've set the gain to 1, so the yellow output and the light blue input signals have the same amplitude of 1 volt. I'm matching the two signals now. Then I slowly crank up the frequency. Around 100 kHz, everything still looks fine. But then, distortion starts creeping in. Near 200 kHz, the amplitude begins to drop. And now, at 1 MHz, it has dropped significantly. With a GBP of 1 MHz and an amplification of 1, the signal should come through better. Eric, have you just told me nonsense?
Well, there is another parameter affecting the bandwidth, the slew rate, which is the maximum rate at which an op-amp's output voltage can change. It's typically the voltage difference between 10 and 90% of the maximum output voltage divided by the time this takes. It's generally expressed in volts per microsecond. If the slew rate is too low, the output voltage can't keep up with rapid changes in the input voltage. And this results in distortion and reduced amplitude. For the MC1458, the slew rate is 0.5 volts per microsecond.
Now let's measure the slew rate and see how it affects the bandwidth. I've added a second op-amp to the left as a preamplifier because the next measurements require signal amplitudes of plus minus 10 volts, which my function generator can't provide. Again, the light blue graph shows the output signal. The rising edge has a positive slew rate of around 900 kilovolts per second, which is 0.9 volts per microsecond. And the falling edge has a negative slew rate around minus 0.7. This is even better than the 0.5 volts per microsecond from the datasheet. Let's figure out how slew rate and amplitude affect the bandwidth. I set the waveform to a sine wave and match the input and output signals. At 10 kHz, these match perfectly. Then I slowly increase the frequency. If we look closely, we notice that above 11 kHz the signals do no longer match perfectly. And the higher the frequency, the more obvious this becomes. So I lower the amplitude to allow the output to reach its peak before the slew rate takes effect. Soon the distortions get less. Finally, at 14 volts, the distortions are gone and the output wave perfectly aligns with the input wave again. I've collected some of these frequency value pairs in an Excel sheet and now I'm gonna let AI do some math. For that I copy-paste the table from Excel into ChatGPT. Let's see what the AI is going to do with it. I'm asking it to plot these points along with a trend line and wait for the things to come. That's wild! It's actually writing a Python program. Just give it a few seconds to run it in the built-in interpreter and voila, there's the plot. Awesome! Because of the logarithmic axis, the data points lie almost exactly on a straight line. Eric, please tell us how you did that.
I found a power line relation between the output voltages and the frequencies. This is the function that I used for the trend line. Well, there already exists a formula for the peak-to-peak voltage as a function of slew rate and frequency. If we write it like this, it looks very similar to the power law model that I have used for interpolation. So B equals -1 and A is the slew rate divided by pi. I've calculated B as almost exactly 1 and A as this value. When you multiply it by pi, you get the slew rate, which comes out to around 670 kilovolts per second, or 0.67 volts per microsecond.
Okay, that's less than we measured earlier, but still more than what's said in the datasheet. We can conclude that the slew rate and output amplitude affect the bandwidth more than the GBP does. That's why many datasheets include a chart showing the maximum output voltage versus frequency. Here's one for the TL081. And here's a chart for the MC1458 again, now with a linear y-axis. So it's not a straight line anymore, but it makes reading the voltage values way easier. So this chart is super handy to check if an op-amp can handle your bandwidth requirements. If your desired frequency and voltages stay below the curve, it's suitable. If they are above, you'll get distortions or you won't get the expected gain. Now let's bring in the gain bandwidth product. For example, if the intended gain is 50, the maximum bandwidth is reduced to 20 kHz. This further restricts the usable frequencies and voltages. I've built all kinds of fun projects using op-amps, like a super simple shortwave SDR receiver on a breadboard, a laser scanning microscope made from old Blu-ray player parts, and even a DIY oscilloscope based on an Android phone and a Raspberry Pi Pico. If that sounds cool, go check out the videos. And hey, hit that subscribe button and turn on notifications so you don't miss anything new. Thanks for watching.